I hope you can see my full screen.
Yes, good.
Great. So let me thank the two organizers for putting together this workshop and allow us to connect in such an easy manner and discuss various aspects of quantum gravity. So I was asked to talk about the interplay of matter and quantum gravity, and I'm obviously very happy to do that. And my talk starts from the very simple observation that there is matter in the universe. And in physics, of course, we should try to take observations seriously when we build our theories. And so this motivates the building of a gravity matter theory. Once such a gravity matter theory is under construction, then of course the next step is to try to understand whether the interplay of quantum gravity with matter then has any, in principle, observable or even already observed consequences for the matter sector. And then that information can be fed back into the theory building, and we can try to build a more viable theory. So that's essentially the logic of part of what I will be presenting here. I will say right up front that I am ignoring the observation that there is time in the universe, which means that I will be talking about a gravity matter theory in Euclidean and not in Lorentzian signature. This is purely for technical reasons. I'm very happy to discuss this more if you want to ask me questions about that. So I'll start with a bold statement that matter matters in quantum gravity. And I think this is a statement that holds across approaches, but I can more specifically provide some evidence for that within the context in particular of asymptotically safe gravity. But first, I'd like to motivate that statement by some more simple examples. The Einstein-Hilbert action is a sort of very simple example for that, because it's perturbatively renormalizable at one loop without matter, but that changes if we do include matter. So it is one example where the UV properties of the gravity theory change once we account for matter degrees of freedom. And of course, you can also view supergravity as one more example where if you include matter degrees of freedom and of course a significantly enhanced symmetry, then the impact of these matter degrees of freedom yet again changes the UV properties of the gravity theory quite significantly. Then an example that comes from a non-gravitational quantum field theory is Yang-Mills theory with and without fermions or without charged matter fields in the fundamental representation. So at one loop, the beta function, and I guess you cannot see my mouse, but I think you can see the first term there. So the first term, the factor of 11, comes from the anti-screening impact of gluons. It means that the pure Yang-Mills theory is asymptotically free. But if you add fermions in the fundamental representation, they have a screening property, and therefore if you go beyond a critical number, which in this case is 16.5, then you actually lose asymptotic freedom. And this is for the case of an SU3 gauge theory here. So this is a particular example where the pure gauge theory, being the analog of the gravity theory, has certain UV properties, and then you add the impact of matter on that, and that very significantly changes the UV properties of the theory. And so that in particular within the context of asymptotically safe gravity begs the question whether it's actually safe to neglect matter. And the answer to that will be that it is not safe to neglect matter, and I will give the answer in two steps. The step one will be just considering the Newton coupling on its own. And its beta function appeared in both of the previous talks in some of the plots. The crucial thing to note here is that the gravitational contribution comes with a negative sign, and that drives one towards asymptotic safety. Vector degrees of freedom have the same type of effect, but scalars and Dirac fermions work against that. And so this clearly shows you again that at least for the Newton coupling, its properties in the UV will depend on the number and the type of matter fields in the theory. There's a number of quite intriguing intricacies in the exact definition of that coupling that I will not go into here. Feel free to ask me about that or take a look at the references that I've indicated. The second step is to obviously enhance the space of the gravitational couplings. And here I will just focus on the Newton coupling and the cosmological constant. This has been extended also to higher order gravity couplings as well as to non-minimal couplings. But let me focus on the plane spanned by the Newton coupling and microscopic cosmological constant here. And what I'm showing you in these three plots is a fixed number of vector fields, namely 12, as in the standard model, a fixed number of scalars, namely 4, again, as in the standard model, and then we are including the fermions generation by generation. And this red dot is the asymptotically safe fixed point, and you can clearly see that it moves under the impact of these meta degrees of freedom. Now that's all very nice, but do these shifts in the fixed point value actually matter? Does it make a difference which of these regimes the gravity fixed point lives in? And so what I will be showing you for a large part of the talk is that there are indeed different regimes in the space of gravity couplings. There is what you could think of as an asymptotically safe traffic light, where there is a region in the gravitational coupling space that is excluded based on results and truncations because of the strong impact of gravity on matter in that region that actually I will talk about how it destroys asymptotically safe fixed points in the matter sector. There is then an orange region in our traffic light, and that orange region does not only rely on the UV properties, it actually needs the link from the UV to the IR. And the orange region then has certain infrared properties that come out as a consequence of asymptotic safety and that are not compatible with the way that matter is in our universe. I'll talk about that in some detail as well. And then there is a region that, as far as we know, is a green region in the sense that from the interplay of quantum gravity with matter, that region seems to be viable. So I will now focus on first explaining the red part of the asymptotically safe traffic light. And that is the weak gravity bound. And let me just highlight there is no relation to the weak gravity conjecture that arises out of the string theoretic swampland. These are two distinct notions. The weak gravity bound is something that occurs purely within the context of asymptotic safety. And it is actually a story of quasi-local operators. And in that sense, it ties nicely into the title of this workshop that focuses on higher derivative and non-locality. So this will be one of the places where sort of non-standard operators actually play a role. And the story of these quasi-local operators starts with an observation that leads to a question, namely the observation that gravity is interacting in the asymptotic safety framework. And then the very natural question to ask is, well, if gravity is interacting, do these interactions percolate into the matter sector? Does the matter sector automatically become interacting if it is coupled to asymptotically safe gravity? And the answer to that question is yes. And the interactions are of a slightly non-standard nature. These are to some extent, or some of those are these higher order, higher derivative interactions. So here I'm showing you some examples for these interactions. For the scalar case, for instance, to the left, you see a 4-scalar 4-derivative interaction with rho being the corresponding coupling. Then you see a 4-fermion interaction. Next, you see something that is a scalar fermion coupling, but not of the standard Yukawa type, but actually also of a higher order, higher derivative nature. And then to the right, you see an interaction for a gauge field that is the standard gauge field term, or includes the standard gauge field strength, but it's actually a gauge field strength to the 4. So it's like a photon self-interaction term. So these interactions, they look pretty non-standard if you look at them with the sort of standard model view. But those are the interactions that are actually necessarily present in a matter sector from an asymptotically safe gravity point of view, which means that all of these couplings in front of these terms have to necessarily be non-zero in the UV in the presence of gravity. And there are then two questions that one can ask about that. The first is, well, why these interactions and not others? And secondly, what are the consequences of these interactions being present? And the second question, the consequences, this is what will lead me to this, to the weak gravity bound and to this red region of our traffic light. So first, why these interactions and not others? There are two answers one can give to that. One is sort of more at a technical or operational level in some sense. The other is a more conceptual type of answer. The more technical answer is the observation that, that these interaction terms that we are looking at here are sort of the kinetic terms for matter squared. And so the diagram that I'm showing you in the center is basically taking just the kinetic term for a matter field. And of course, gravity, given that it's coupling to any form of energy or matter, gravity couples to the kinetic terms for matter and then forms loop diagrams like that take the kinetic terms, and out of that they build interaction terms. And so this is the structure of the interaction terms that you see on top. It's generically the kinetic term squared. There's a more conceptual answer that one can give to the question why these interactions, and it ties to a whole other interesting story that I don't have time to go into. That is the story of global symmetries in quantum gravity. Within asymptotically safe gravity, there are good indications that global symmetries of the matter sector really shape the gravity-matter interplay. And it is true that these particular interactions that I'm showing you here are the type of matter interactions that respect a sort of maximal set of global symmetries for matter fields. For instance, scalar fields, for those, the kinetic term actually satisfies a shift symmetry, and that same global shift symmetry is actually preserved in the interaction term that we are looking at here. So there is this more conceptual answer. Why these interactions? Well, because these are the ones that are determined by certain global symmetries that the gravity-matter interplay has to satisfy in the most symmetric incarnation that it exists in. So this answers the question, why should we look at these specific non-standard type of higher order operators? And now the second question, what are the consequences of these operators being present? And here I would like to go back to the diagram that I showed you previously, that is a representative of diagrams that induce these interactions. And on the right-hand side, you see the corresponding beta function. And I'm highlighting two terms out of the full beta function. The right term is just the matter self-interaction, and the term, the first term in the beta function is one representative of a term that comes from this gravitational contribution that is tied to this diagram that I'm showing you here. And you can see that that has quite an interesting effect in the sense that the beta function for this matter coupling is a parabola that is being shifted upwards under the impact of quantum gravity. And you can see on the left in the plot that if you make the gravitational contribution strong enough, then you have shifted this parabola such that there are no real zeros. In other words, there isn't asymptotic safety. So to summarize, what that means is that if we have an impact of quantum gravity on these matter couplings that is too strong, the gravity contribution being too large, then you destroy fixed points in the matter sector. In other words, in that case, strong gravitational interactions actually trigger novel divergences in the matter sector. And that actually means that by looking at the interplay of quantum gravity with matter, we learn that asymptotic safety appears to not be realizable in a strong gravity regime. That is the regime where the Newton coupling is large enough, but you can also see from the first term in the beta function that you can reach such a regime if you go with the microscopic cosmological constant towards larger positive values. And so this is how, from the interplay of quantum gravity with matter, we conclude that there is a region in the microscopic gravitational parameter space that doesn't appear to be compatible with asymptotic safety really in matter gravity theories. And of course, let me stress at this point that as both of the previous speakers, I'm working within truncations of functional renormalization group flows, which means that there is a systematic uncertainty attached to the results here. So now I've highlighted the red region of the asymptotically safe traffic light. Now what about the orange region? What about this other bound? And for this, it's important to understand the predictive power of asymptotic safety. This also ties back to some questions that were already discussed in the chat and after Frank's talk. And I would just like to take 2 minutes to highlight the predictive power of asymptotic safety, the general idea behind that, before I go back to apply it and explain where this orange region here in the parameter space comes from. So asymptotic safety is just nothing but a certain form of symmetry, namely quantum scale symmetry, that is realized in the UV. But then if we look around us, we can clearly see that there's a lot of distinct physical scales that exist, which means that we don't live in a scale symmetric world, which means that there has to be a scale at which a departure from scale symmetry sets in. And now such a departure happens along the relevant directions of the renormalization group flow of that fixed point. And a simple toy model for a beta function to show you such a relevant direction is the one that I'm showing you on the bottom, which features an asymptotically safe fixed point that is infrared repulsive in this coupling, which means that for this configuration, quantum fluctuations actually drive you away from scale symmetry. And if you demand scale symmetry in the very far UV, so you start from the fixed point, then still in the infrared, there is a whole range of coupling values that opens up that you can reach starting from scale symmetry in the UV. In other words, there is no prediction tied to such a relevant direction. And that is the other way around for the irrelevant directions. And you get a toy model for that by just flipping a sign in the beta function. And here, quantum fluctuations drive you towards scale symmetry, which means that if you demand scale symmetry in the very far UV, then from that, you get a prediction of the value of the coupling in the infrared. And so this is where the predictive power of asymptotic safety comes in. And this link between scale symmetry in the UV and the corresponding prediction for coupling values in the IR, this is what will play a role for the quantum gravity matter interplay. Of course, the story is a little bit more complicated than these one-dimensional panels I've been showing you. We have a number of different couplings in our theory space. And so the story generalizes to a higher dimensional setting where demanding asymptotic safety in the UV restricts you to lie within the UV critical surface, which is this purple hypersurface in this plot here. And you can see that demanding that you lie within that surface so that the UV really is scale symmetric, that fixes the value of the irrelevant direction. In this case, it fixes the value of the coupling G3 once you have determined G1 and G2 by experimental input. And one way to think about this UV-IR connection is in some sense that scale symmetry is, of course, only realized in the UV, no longer in the infrared. But a remnant or an imprint of that quantum scale symmetry remains in the infrared in the form of relations between couplings that are satisfied in the infrared because the theory starts off at a scale symmetric point in the UV. You can also just think of that in some sense as the predictive power that any new symmetry that you impose on your theory will bring. Any new symmetry will typically constrain the values of your couplings or result in relations between interaction terms. So this idea can now be realized in the context of gravity matter theories. And here in the UV, we start with a setting that could be something like the standard model plus gravity, which then has an asymptotically safe fixed point. At the Planck scale, gravitational fluctuations decouple dynamically because the dimensionless Newton coupling falls off as k squared. And so you dynamically transition from a theory that has a strong impact of gravity to a theory that is then in the infrared, really just a pure matter theory. And the logic now is as follows. To connect to that traffic light, some of the couplings in the matter sector will correspond to irrelevant couplings, which means that from the scale symmetry in the UV, we will get predictions for their values in the IR. And those can then be compared to experiment. And because the values of the infrared predictions depend on the microscopic gravitational couplings, they give rise to constraints on the UV structure. And this is where the orange region in our traffic light will come from. And I will explain that in the next few minutes. As a proof of principle, I'll talk about Yukawa couplings and then very briefly say something about dark matter in a second step. So for the proof of principle, let me talk about Yukawa couplings and the impact of gravity on them. So this is a busy slide. Let's start on the top. We see the beta function for a Yukawa coupling with just the one loop term and then the gravitational contribution. And this Fy summarizes the impact of gravity in the Einstein-Hilbert truncation. I've given you the form of the Fy further down on the slide. Because this is a lengthier expression, I will just be parameterizing the impact of gravity just in terms of this parameter Fy, but it depends on the gravitational couplings. This Fy is then constant above the Planck scale and then switches off dynamically below the Planck scale where gravity decouples. And now what we see is that if Fy is larger than 0, then the beta function for the Yukawa coupling features a free fixed point that is asymptotically free, because this is where the Fy term dominates and has the beta function start off with a negative term. And then at larger values of the coupling, the matter one loop term kicks in, the Y cube term kicks in, makes the beta function positive. And so these two terms, the gravitational and the matter one, they balance out at an asymptotically safe fixed point in between. So what that means more specifically is that in this beta function, matter and gravity couplings, matter and gravity fluctuations compete. If gravity fluctuations are strong enough, then the gravitational term, the Fy term, wins and makes the theory asymptotically free. On the other hand, if the matter fluctuations dominate, then we have the usual triviality problem for a Yukawa interaction, and we're just getting UV unsafe trajectories. And that, of course, can happen if matter is strong enough to dominate, so if the Yukawa coupling is large enough. And then in between, these two can balance out at an asymptotically safe fixed point. And at that fixed point, the Yukawa coupling corresponds to an infrared attractive to an irrelevant direction, which means that by demanding scale symmetry in the UV, we can then link that to a unique value in the infrared. So this is a particular example for the predictive power of this new symmetry at play here. Now let's briefly switch to what happens if we don't consider, as we did here, Fy being larger than 0, but Fy being smaller than 0. In that case, both matter and gravity fluctuations work towards triviality. And all trajectories which feature a non-vanishing Yukawa coupling are UV unsafe. And that means that there is exactly one trajectory which can realize a form of scale symmetry in the UV, and it's the one where the Yukawa coupling vanishes always. And now let's take a brief look at whether that is at all compatible with the structure of matter in the standard model. And the LHC has, of course, measured a number of Yukawa couplings, most importantly, the top Yukawa coupling to be non-zero. And so if we want to ever be able to accommodate an observation like that into the theory, then we are restricted to a region of parameter space where Fy is larger than 0. And this is what then in this traffic light generates this orange region. The orange region is one where there would be an asymptotically safe matter gravity fixed point, but one which gives rise to a vanishing Yukawa coupling at all scales. And that does not appear to be very compatible with the phenomenology of particle physics that we observe. And so this then leaves us with a more restricted region of the gravitational parameter space in which an asymptotically safe fixed point could lie. There are extensions of these ideas to somewhat more realistic models, but for reasons of time, I will not go into that. Instead, I would just like to highlight that in the beginning of the talk, I showed you that the impact of matter shifts the gravitational fixed point around. And now I told you that there are these two regions in the gravitational coupling space that are excluded based on different types of considerations. And so now, of course, it's interesting to understand where in these regimes of the gravitational coupling space the fixed point actually falls into. So if we start with one generation of fermions, we are in one of the orange regimes. We remain there for 2 generations, but we enter the green region for 3 generations. All of that, of course, with the word of warning that these are results within truncations, so they come with systematic uncertainties. But I would say that this is a promising indication that these type of ideas could pan out and warrant more in-depth investigations. Roberto, can you briefly let me know whether I have about 4 minutes or 5 minutes left?
Okay. Sorry, I was muted. Yes, you have 5 minutes.
Excellent, thank you. So I would then like to take these 5 minutes to sort of make a bit of a jump. So I'm skipping a part of the story on more of the interplay of quantum gravity with the standard model. I'm happy to answer questions about that, but I would now like to go beyond the standard model and take a look at dark sectors and give you the asymptotically safe perspective on that, because I think that's an intriguing story where there's lots of open questions to tackle from this perspective. So the standard model and gravity on its own is probably not sufficient to describe all observations in our universe. I say probably because we don't really know which additional degrees of freedom the gravitational sector could actually harbor and whether they might potentially be enough to explain observations. But typically we would assume that there needs to be, for instance, a bunch of additional dark degrees of freedom to provide dark matter, to potentially provide some form of dark energy, and to answer some of the extra questions in particle physics that arise. But then, of course, the question is how many new fields are there, which interactions should they have? And there's just a huge forest of different models out there. And on the other hand, there is, of course, a lack of discovery to date. And let me take a very bold interpretation of that lack of discovery, which would be that it's time to think about new theoretical paradigms. And so what I would like to test out a little bit is whether the asymptotic safety paradigm could be a candidate for such a paradigm to provide us with a novel view of dark matter and its nature. And so in the spirit of that, I will introduce you to some ideas on asymptotically safe constraints on dark sectors. So to start with, the first question is, how many new fields do we want to add? The impact of matter on quantum gravity suggests that it should be safe to add a few additional new scalars and fermions. We are not sure how many more we can add, but we think a few should be safe. So let's start with the very simplest model, which is just the Higgs portal to one additional singlet scalar S in the dark sector. The impact of quantum gravity on that is quite an interesting one, because quantum gravity actually drives the portal coupling between the Higgs and this dark scalar to 0 at the Planck scale. That's part of a more general set of results that quantum gravity tends to flatten scalar potentials, which can have quite intriguing consequences in a number of contexts. What it means for dark matter here is that this dark matter candidate, this dark scalar, decouples and cannot be produced as a thermal relic. And therefore, a single uncharged dark scalar as a thermal relic with the Higgs portal is incompatible with asymptotic safety. And I think that's a nice example for the predictive power that this approach could have, that would really allow us to say that certain types of meta models might just not be compatible with asymptotic safety. So this could be one example. Of course, this then motivates to ask whether one can extend the model in some way to make it compatible. And here we then go to sort of the next more complicated model by adding an additional dark fermion. And let me be very brief on the story here. What I would just like to highlight is that we are looking at the toy model for the standard model, where we just take a scalar for the Higgs and the fermion for the Yukawa coupling into account. We are neglecting the whole gauge sector. And then we are including a dark sector, which is also a scalar and a fermion. And then that model has a whole bunch of different interactions and different couplings. And then something quite intriguing happens under the impact of quantum gravity, namely that a fixed point is being generated in all of these meta-couplings. And most of these meta-couplings correspond to irrelevant directions of that fixed point, which means that demanding scale symmetry in the UV gives us predictions for the values of those couplings within that toy model in the infrared. And it turns out that, in fact, as a function of the dark scalar mass, you can predict the dark fermion mass, you can predict the portal coupling from the dark sector to the visible sector, you can predict the dark self-interaction, you can predict the mixing angle, and also the non-minimal couplings. So essentially, what would be a model that has quite a number of free parameters if viewed from an effective field theory point of view becomes highly constrained under the impact of quantum gravity. And that, of course, also means that there's a more concrete idea where you would have to look for such dark sectors in this larger parameter space. But it also, of course, means that this would be a good portal to actually rule something like asymptotic safety out. So the upshot of the dark sector exploration so far is that there seems to be quite a high predictive power of asymptotic safety for these type of models, which would lead us to believe that the simplest dark sector model could already be excluded, and there are quite significant constraints on extended models. And again, all of this, of course, within truncations of the functional renormalization group, and also still with the caveat of this being in Euclidean signature. So you should view this more as a proof of principle instead of something where you should take the actual numbers too seriously. There's more news on meta-gravity systems where a lot of interesting things are happening that I didn't have time to cover and review. I would just like to highlight that this is in general a space that could be worth watching. And before I conclude, let me just highlight the team thanks to which all of this work has been possible, many of which have now moved on to other places, and some of whom you have or will see at this conference. So thanks to their initiative and dedication. And as conclusions, let me just say that this link between theory and observations, where we try to deduce observations from theory and then feed back experimental input into the theory to make it better, that is, of course, a real challenge in quantum gravity, but that there could potentially be a meta portal that allows us to achieve at least a few steps along this way. And so with this, I'd like to thank you for your attention.
Thank you, Astrid. There had been a couple of questions in the chat, so I will start from Anish Ghoshal.
Hi.
Anish, yeah.
Can you hear me? Hello?
Yeah.
Yes.
Oh, okay. No, so I have a small curiosity. So when you're computing the beta functions, have you also tried to see what happens in first order formulation of gravity? Like what happens to the beta functions from the gravity sector if you take Palatini gravity or something like that? Because essentially you will have more fundamental degrees of freedom there, right? So might be the beta function suppressed.
So within the pure gravity setting, a number of different sort of alternative setups, first order formalism, the impact of torsion and so on, has to some extent been studied. In the interplay with meta so far, the focus has been mostly on really just metric gravity. The case of unimodular metric gravity, which might or might not be a slightly different setting, has been explored to some extent. But so far, we've sort of worked from the assumption, or this work has started from the assumption that observationally, we don't yet have any indications that there is a necessity to extend the fields in the gravitational sector beyond the metric. And so therefore, we stay with the most conservative set, which has the fewest extra degrees of freedom.
I see. Thank you.
Richard?
You at several points mentioned running equations that involve the numbers of scalars. I'd like to know what kind of scalars, well, first off, does it matter what the conformal coupling of that scalar is? And if so, what conformal couplings were you assuming?
Yeah, so in a part of the talk, when I was just referring to the impact of minimally coupled scalars on gravity, that was of course just with the minimal coupling, non-minimal coupling set to 0. In the latter part of the talk, I had, for instance, in this in the setting here with the dark sector, we had a non-minimal coupling. The fixed point value does not lie at this conformal value. So it's a fixed point value that lies at a finite value, but away from the sort of special conformal point.
Philip?
Oh, yes. Astrid, I endorse your view that matter matters for quantum gravity. In fact, I make a case that it even matters completely in the following sense. If you look at a gravitational equation, you write a gravity piece equals a matter piece. And the matter piece is intrinsically quantum mechanical. So if you think of expanding not as a power series in the gravitational coupling, but as a power series in Planck's constant, the matter side begins at h bar to the 1, and there's no h bar to the 0 term. So my view is that there should also be no h bar to the 0 term on the gravity side either, that classical gravity is output to quantum gravity, not input. And when I do that, I finish up with a sum rule, which basically gives me some relation between the wave function renormalization constant of the graviton and that kind of series you had where you had a number of fermions, a number of scalars, a number of bosons, and so on. And it's a different formula, but it's a constraint on the matter sector to make the wave function renormalization constant be positive in much the same way as your constraint is to make the sign of the beta function be negative. So I just thought I'd comment on that.
Mm-hmm. Maybe I can just expand a little bit. I would assume that most quantum gravity approaches do have constraints just of a sort of similar form where certain requirements of the gravity theory will be impacted by the effect of matter and therefore give rise to constraints, for instance, on the number of matter fields. And of course, if that was something that we could systematically look at various quantum gravity approaches, then that of course would be a nice way to understanding which of those are distinct mathematical formulations of the same theory and which of the quantum gravity approaches are really physically distinct in their predictions.
Okay, there's one more question by Alexei, and then I would suggest that we postpone any other question to the discussion. So Alexei, please.
Yes, thank you very much. And thanks for this nice talk. Actually, I'm, well, maybe I'm a bit far from this, but just a short question about all of that. What would be most realistic, the shortest term idea, what you're going to predict with this mechanism which you highlight in your talk? What do you want us to see?
Great question. So I think that there is the one of the challenges that we are facing with this is that at the moment we see sort of promising structures, but if you would really want to have specific numbers, then of course, for instance, the question of Lorentzian signature would be something that would have to be resolved. And also in general, I would say the question of really getting sort of, robust, numerically robust predictions out of that. And so here, maybe I can just go back to that slide to highlight that here. I think one thing that we really need is to take together different methods from which we can sort of robustly confirm that the same type of results really emerge from different settings. And here there's quite interesting developments on the lattice. Then of course, sort of, the dream scenario would be to understand that, for instance, the standard model as it is just is not compatible with this approach because some of the predictions just really don't pan out, and then understand what is it exactly that we have to add in a dark sector in order for these predictions to pan out. But of course, that is a bit of a sort of hopeful dream.
I see. Thank you.
Okay, so on this dream, we close this session, and we thank Astrid again.